Yes, the session is now recording. So, so good evening, everyone. Welcome to the ninth weekly problem solving session for the Physics of Nanoscale Devices NPTEL course. My name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, in this ninth week, we are going to kind of continue from where we left off in the last week. So, this is not a new topic per se. So today what we are going to do is we are going to try to derive the various MOSFET characteristics. So in last week's session, we kind of considered an ideal MOSFET and we were trying to see what the various non-idealities that may occur in a MOSFET are. And we qualitatively understood what is going to happen when there are effects like subthreshold swing or DIBL, and how it affects the behavior below the threshold, or how it shifts, kind of essentially shifts the threshold voltage, or how it serves to introduce like a non-constant saturation current and things like that. So when we talk about MOSFET characteristics, we are talking about these things: ID versus VGS, oops, IG versus VDS, or ID versus VDS. So these are respectively the transfer and output characteristics. So our primary focus is going to be to kind of now get a quantitative idea. And still, even now, we are in the regime of the classical MOSFET, long channel MOSFETs. And then we will, what to say, like look at the linear and saturation currents. So that is essentially part of the output characteristics of the transistor. And then we shall look at the notion of the thermal velocity in a ballistic channel. So at this point, we will switch over. We will leave the long channel devices behind, and we will look at the ballistic channel and see how to kind of move these ideas over. Essentially, the notion of saturation, the notion of channel pinch off. Like if I have a nanoscale channel, is channel pinch off even going to happen? If channel pinch off does not happen, then how does saturation behavior set in? Where do I have my threshold voltage from? So these are kind of the ideas we will be looking at in the next week, but this discussion on the thermal velocity will serve as a starting point for that. So just to like remind the people of some things from the slides. So these are long channel MOSFET, so it is assumed that most people are familiar with how these devices operate. So yeah, just let me choose the right color. I think black would be good for this. Yes. So typically, when we are looking at a depletion mode MOSFET, we have the source, the drain, and we have a channel in between. So this is a oh, this is a P MOSFET. Okay, yeah. So this is a P MOSFET because the wait, why is this N here also? Strange. This should have been P because this is N and N over here. Whatever. Like these are minor typos. You can kind of what these are. So when we have linear in the when the device is operating in the linear regime, what we know is there is an inversion layer that forms in the channel. This inversion layer is a quickly try to line out. So just to contextualize the things that we have been looking at throughout the course, this is a quasi 2D channel. So even though this is a three-dimensional, this is a bulk long channel device, ultimately the channel is a quasi 2D channel because there is only a thin layer where the charge inversion takes place, and that those inverted charges take part in the conduction between the source and the drain. So that is how the device operates in the linear region. When we are talking about saturation, then classically we know there is this phenomenon known as the channel pinch off. Essentially, the concentration of charges in the inversion layer keeps reducing as we move from the source to the drain. It becomes smaller and smaller and smaller, and at a certain point, it comes down all the way to zero. When this starts happening, we say that the current has started to saturate. So, and again, like for conventions, we will assume that this direction is the x-axis, and the moving from gate through the substrate is the y-axis, and moving from the source to the drain is the x-axis. And the source channel interface will be taken as x equal to 0 for reference purposes. And we will also kind of assume that, no, yeah, it's a weak assumption, although we will not be invoking it too much. The length of this gate layer will typically be considered to the length, considered equal to the length of the channel. Although we will not be using that concept exactly today, maybe next week when we are looking at the electrostatics and other properties, we may invoke that idea. Essentially, what I'm trying to say is this length L is also the length of the gate layer that is present for the device. Like that should be more or less apparent from the figure itself, but just to be precise. So this is considered to be equal to the channel. The reason for that again should be clear once we reach that point. So we have this pinch off region. So now let us look at how the like how we can at least uh, in a semi-classical route go and derive the various characteristics of the MOSFET. So first we are looking at the MOSFET current in the linear regime. So we are in this case. So the linear regime current IDS is given to be W times W is the width. Let me switch colors. Yeah, so this is the width of the channel essentially. That is the width is in the, like, it goes into the plane of this figure, into the surface. So the width is along the depth of this image. Okay, so this is the channel width multiplied by the amount of charge that is present in the channel multiplied by the average velocity. So we are taking a fairly straightforward approach. The charge into the velocity is going to give us the surface current, and because this quantity is essentially coulomb per centimeter square centimeter. So this is charge per unit area. So if you look at the dimensions, ultimately when all of these are multiplied, we will get charge per unit time, which is ampere. Okay, so one more thing that we need to understand is in the linear regime, of course, here since this is the linear regime, this also implies IDS is proportional to VDS. I mean, that is essentially why we are calling this the linear regime. Now, if you go back and look at the ballistic MOSFET case, we know that this proportionality occurs for, so this condition is true for small VDS. So similarly, even for the bulk MOSFETs, VDS needs to be small. So since in this equation, Q, the charge is stored in, charge depends on the gate substrate or gate source voltage and the drain source voltage. Now since VDS is very small, we can say to a reasonable extent that the charge is dependent only on the gate voltage and the oxide capacitance. So this layer here, so this layer here acts as a mass capacitor. Again, this is a concept, this is an idea that many of you would have studied in other courses, like any semiconductor devices or basic device theory course will cover this. In any event, next week we shall be focusing more on this. So for now, what I can say is this quantity, this structure here, like essentially, if I'm looking at it this way, uh, if I say, if I'm looking at, and then yeah, so this is my metal layer. So this is metal, and this is the oxide layer, and this is the semiconductor layer. This is the substrate essentially. So over here, I can see that this pretty much operates like a capacitor. So I have a VG applied here, and I will have, if I close this quantity here, not quantity, this part here, and I say some Vs, then there is going to be charge accumulation here and here. If I assume Vg is positive and this is negative, then I'm going to have positive charges forming along this layer. I will have positive charges forming along this layer, and we shall have electrons lining up along this side. So the oxide in the middle acts like a dielectric. So now these accumulated electrons can be pushed from the source to the drain via a drain source voltage. That is essentially the idea of a transistor, like a field effect transistor. Not every transistor. BJTs operate on different principles. So, and we also know that this accumulation occurs only for Vg greater than Vt. Again, more details on this next week. But some of you may already know this. Some, if not all of you, may already know this. That up until I reach the inversion voltage, this kind of charge separation will not occur in the system. However, once I exceed Vt, then we will have a case where this thing starts acting like a capacitor. So essentially, I'm just writing this as Q equal to Cv. The threshold voltage tells me at what point charge accumulation will start, sorry, the charge inversion will start occurring in the channel side. So Q is given by Cox times Vgs by Vt. However, we will be more interested to know the charge density, sigma. So sigma is equal to, so here Cox by A times Vgs minus Vt. So this Cox by A is the capacitance per unit area. And this quantity sigma is the surface charge density. And oh yeah, now the average velocity in the channel, now this is a very classical expression, because like again, Drude-Sommerfeld model, or classical macroscopic conduction, we write the electron velocity v is equal to mu times E vector, where this is the mobility, and of course the electric field. So, and this is equal to minus dV by dx. So we'll write it like this. Now this is the variation of the potential along the x-axis. Now for small VDS, what I can say directly is, since the change in VDS is very small, VDS is small, then I can automatically say that is minus VDS by L, because there is only a very tiny change, and since it is so small, I can just average it very easily because there isn't much of a variation. So from this I can also readily write V average is equal to minus mu VDS upon L. So substituting this into this, we will get the expression for the linear current. So now let us solve some problems to see how these values turn out to be, what these values turn out to be. So first, we are given a long channel MOSFET with channel length 1 micrometer, channel width of 10 microns, and the oxide capacitance is 3.45 into 10 to the power minus 7 farad per uh, centimeter square. So this is capacitance per unit area. Now, first question is calculate the charge density if the threshold voltage is 0.7 volts and VGS is 5 volts. So in this case, yeah, so the charge density is going to be, can be calculated like this. So the charge density sigma is equal to VGS minus VT. Just one second. Yeah, so now this quantity here is going to be 3.45 into 4.3. 4.3 is VGS minus VT into 10 to the power minus 7. Oops. Yeah, so now this will give us approximately, this will come out to be like, this is 3.5, so 4 times that is going to be 1.4, and another third is going to be another 0.1. So this will approximately be 1.5 into 10 to the power minus 6 joule per centimeter square. Now, yeah, so this is the uh, surface charge density in the channel when the VGS, when VT is 0.7 and VGS is 5 volts. So this is a fairly straightforward calculation. You will notice that in this problem, the channel width and length are kind of extra information. Like, we have not used it anywhere. So to use that, we have the follow-up question, which is in the previous problem, calculate the current flowing through the channel if the drain source voltage is given to be 1 volt and the mobility is given to be 800 centimeter square per volt second. So this is the unit for the mobility of the electron. and the drain source voltage is given to be 1 volt. So since VDS is equal to 1 volt, the electric field will be 1 divided by 1 micron. So this is going to be like, you know, in appropriate units. You will see that we don't even have to bother calculating these quantities. So this is the electric field, therefore, which implies, sorry, this implies the average velocity is going to be 800 into 1 divided by 1 micron. 1 volt divided by 1 micron. You can see that the volt has cancelled each other, and there is another length dimension that is cancelling it out. So now to this I need to multiply the width of the channel. Therefore IDS. Now just to bring this whole thing, tie this whole thing up together, I will write the full expression here. W times Cox into VGS minus VT into mu times, is there going to be a negative sign? Yeah, of course there's going to be a negative sign. So mu times minus, or you know what, minus VDS by L. So this is the full expression for the current, and again, as you can see here, IDS is proportional to VDS. So here we can directly see that. So this is in the linear regime. Now we know this quantity, we know this to be 1.5 into 10 to the power minus 6. So ultimately the answer is going to be 10 micron into 1.5 into 10 to the power minus 6 into 800 and 1 volt divided by another 1 micron. So I'm writing the symbol mu here just to indicate that there is a power of 10 to the power minus, like there is a factor of 10 to the power minus 6. But as you can see, that is going to cancel out readily in this case. And ultimately, all the other values are set to 1, like I've chosen the parameters very conveniently. So what we are going to have is 800 times this, and the all the other units, as you can see, will cancel each other out rather conveniently. The micrometer and micrometer go away. There is a centimeter square here, and this is a coulomb per centimeter square, so even those things cancel each other out. So this will give me 8 into 1.5 is going to give me 12. So this is 1200 into 10 to the power minus 6, and the unit is directly going to be ampere. So this is going to be 1.2 milliampere. So this is the current that flows from the drain to the source. And you can intuitively see, not intuitively, you can see that our choice of parameters here is kind of appropriate, because typically when we are looking at the drain source currents, it's going to be in the milliampere regime, if not lesser. So the values are fine. Our choice for VDS, our choice for the VGS and oxide capacitance, and all of these are more or less equal. In fact, this problem I kind of like reverse engineered from an old a solved example in semiconductor devices textbook. I just took that problem and broke it into 2 or 3 pieces to make this problem. So typically you will have questions such as this appearing in your assignments. Now, so this more or less explains what the linear characteristics are. So I need to calculate the depletion, the inversion charge uh, concentration. So that depends only on VGS, of course, by how much VGS is above VT. So let me just, you know, add a new slide here and write those points so that they can serve as a reference. So if you are looking at the linear regime, the things that we need to remember are the following. Q, or rather sigma channel, is proportional to VGS minus VT, and then the velocity is proportional to VDS and also proportional inversely to the length. So from this we can also see more notions. The longer the channel becomes, the smaller the so I'll write that here. IDS is proportional to VGS minus VT, and of course IDS is proportional to VDS. This is the reason why we call it the linear regime. And one more curious factoid is this is inversely proportional to the length. The higher, the greater the length becomes, the lower the current will be for the like for the same VDS. And this is also to be expected because in the linear regime, I expect my channel to behave like some kind of a resistance. So the longer the resistance becomes, the greater its value of resistance will be. It's linearly proportional. So if I double the length, the current will be half because the resistance is going to be doubled. So all your calculations in the linear regime are going to be fairly straightforward. And the width of the channel is, another thing is IDS is proportional to width of the channel. Again, this we can take from the analogy that the width for a quasi 2D channel, the width plays the role of the surface area. So the more I increase the surface area, the less the resistance will become, therefore more the current will become. So in a way, not in a way, we can actually see that in the linear regime, the current actually depends on the aspect ratio of the channel. Like, it's actually a curious little relation. IDS is actually proportional to W by L. And the more, inverse of the aspect ratio, because yes, typically we'll write the aspect ratio as length is to width. So this is the inverse of that. So the narrower my channel is, the lesser current it will conduct. The wider my channel becomes, the more current it will conduct. So we can see that the kind of ideas that we developed for the ballistic MOSFET, where we said that yes, the broader the channel is, the more half wavelengths it can accommodate. So the more modes it will have, more modes implies more currents. In a way, that concept is being generalized for the bulk case as well. Like essentially, what we know is that just 1 second. Apologies for the interruption. Yeah. So what we can see is the ideas that we developed for a ballistic MOSFET, the trends more or less follow even if we look at a classical long channel MOSFET. So we can see that the concepts that we've developed for the ballistic MOSFET essentially give us the similar behavior to the long channel MOSFET as well. And this is an encouraging sign. Now we shall look at the saturation regime. So In the saturation regime, it is identified like essentially how do we identify this region if we are trying, characterization experiments. IDS will become more or less constant with respect to the increase in VDS. Or in other words, IDS increases, it actually increases in a realistic device sublinearly. So, what does sublinearly mean? So the idea of sublinear variation can be seen as follows. So in the linear regime, I will have the current increasing linearly. So this is the linear regime. So here, of course, this is the output characteristics of my MOSFET. So this region is linear where IDS is proportional to VDS, and after this, the increase will kind of not be linear anymore. It's going to become something like this. Had it gone on to increase linearly, just one second, the current would have increased something like this. Now the rate of increase has actually tapered down. It is no longer increasing at the linear rate. The rate of increase has kind of fallen and it is no. And it will increase nonetheless, but it is not increasing as fast as a linear function. It is increasing slower than a linear function. So like if you are thinking about it in terms of powers of VDS, in the linear region IDS was proportional to VDS or VDS to the power 1. So here I have proportional to VDS, shouldn't look like alpha. Otherwise, people reading might get confused. Yes. Now here, it is actually proportional to, oh no, it is actually proportional to VDS to the power some k, where I know k is less than 1. So I know this. Of course, it is not 0 because it is increasing. So it is a fractional value. Realistically, this is what the saturation regime will look like. Now, why is this happening? So for this, let me see. So next we are again looking at a problem. So fine. Yeah, so most of our discussion is going to be in the derivation of this classical saturation current. Okay, so uh, yeah, just one second. Yes. So one thing we know is the saturation current is given by this expression. W by 2L dash mu n C ox into VGS minus VT the whole square. Now, what we know is this is caused due to the pinch off of the channel at higher values of VDS, thereby reducing the length of the inverted channel. So, now what does this mean? So, before we go on to the problems, let me just make a new slide and bring this up here. Let us like take some 15-20 minutes to kind of have a focused view of what's happening. Like, yeah, although this is technically not a problem and may not be very helpful in solving assignment like numerical problems, it will help you with many of the theory questions. So that's why I intend to take a little bit of time to discuss this. Yeah, so I have my substrate over here, and in this substrate, I have my source and the drain. Of the source and the drain. So this is the source, this is the drain, and on top of this, we have the uh, gate layer, the metal oxide layer. Oh God, fine, this will do. Yeah, so now over here, we are applying a VG, and of course, there is a Vs here and a Vd here. Now, if Vg is greater than Vt, now for the device to be on, I need Vg greater than Vt. And in that case, we are going to have a layer of depletion charges. Now, what is the effect Vd will have on this system? Now, let me assume to do this analysis, let me assume this quantity is 0. So, first assumption is assume Vs is equal to 0. Okay. And as I told before, this terminal is the positive plate of the capacitor. So this is essentially the positive capacitor plate and this is the negative capacitor plate. Now we know VDS is greater than 0. Which automatically implies VD is greater than 0. Therefore, now think about it in terms of proximity. In this region, close to the drain, the voltage, the negative, essentially the effect of the positive voltage on this side. So this is the positive capacitor plate. The positive voltage will kind of be reduced, nullified by the drain voltage. Okay, so VD lowers the effect of VG. This implies it reduces the inversion charge concentration or inversion charge density. Now remember, I have my current, that flows in this direction. So IDS flows in this direction because it is the drain source current. Now we know that uh, we are going back to this minus 1.2, like there's a negative sign here because I'm essentially trying to measure the flow of, like, this gives me the flow of electrons. So the current will always flow in the opposite direction. Okay, so here all of this quantity gives me, so let me just write it here. Sign is dropped as essentially what we calculated here through and through was the velocity of electrons, like velocity, and we use the mobility of electrons, we evaluated the velocity of electrons, and we saw the electron flux. So this quantity is going to be not IDS, but rather it is going to be negative of IDS. Okay, as the expression gives the flow of electrons, E minus. Okay, so yeah. Okay, so coming back, so it reduces the inversion charge density. So now what is going to happen? When we apply a voltage, the electrons are going to move from the source to the drain. So I'm going to have my electron flux that is effectively moving in this direction. Now, when these, and of course the energy the electrons gain will be proportional to or will depend on VDS, of course VD in this case, because I've set Vs to be 0. Okay, now, but another thing that we need to like note here is, not another thing, as a result, higher the value of VD, sooner the, so this reduction is essentially what we call as pinch off. So this is the idea of pinch off. Essentially, when my, so let me make this diagram slightly bigger, then then I'll be able to, and let me use a, what, let me use red for now. So this is the, this is the inversion layer. So this is, now let me switch over to a different color. Let me take this one. In the presence of VDS, this looks too similar. Does this look different enough? Yeah. So in the presence of VD, what happens to my channel? This is what will happen. Eventually here, the charge density will get pinched off. So the red line in the above figure, this is inversion layer for small VDS. Let me just box this off. Come on. Yes. Inversion layer for small VDS, whereas the yellow line is the inversion layer for large VDS. So now the electrons are kind of accelerated or driven by VDS from the source to the drain. Now when VD becomes very large, essentially I have an opening that forms here. I have an opening that appears here because of the pinch off, and in this region there are no free charges. So there are no free charges. So essentially what happens is, since there are no free charges here, I can use Gauss law. I can essentially make a Gaussian surface over here and say the following. No free charges implies the electric field becomes zero, because the electric field flux is proportional to the charge density. Since there are no free charges after the pinch off, the electric field will become zero, which further implies no electron acceleration, which means the electron velocity gain, acceleration, no accelerations, is acceleration, or electrons stop gaining energy. And that is what happens here. After the pinch off starts occurring, not start, did I write start? Stop, yes. So had the electrons been gaining energy linearly, it would have been increasing like this. But since the pinch off has occurred, it is no longer gaining energy at the same rate. So it is no longer having the velocity. Since it does not have the velocity, the current will kind of taper off. Now, why is it still increasing? It is still increasing because even though the current has tapered off, the channel has been pinched off. The VDS is still supplying enough kinetic energy for the electrons to punch through. So that is what is happening here. When I have my saturation current, I have my electrons coming through here with a very high velocity, and they kind of traverse through this neutral region to reach the drain. And of course, as we know in the case of even our standard PN junctions, not all the electrons will make it to this side, and that is what we see as a saturation here. Previously, every electron that was starting from the source was making it to the drain. Now, because of the channel pinch off, a fraction of the electrons do not make it anymore. So that fraction essentially leads to a reduction in the rate of the current increase, and that gives us the notion of current saturation in a classical MOSFET. Sooner the pinch off occurs. So pinch off, let me just write these things also, reduces the number of electrons reaching the drain. This implies the current increases at a slower rate. Yeah. Okay. Now derive the expression for the classical saturation current in a MOSFET. How do we do this? We can do this through the following method. So first thing we need to do is first introduce the effect of the drain voltage. Okay, so first thing we will do is to account for the drain voltage. Effect of VDS. I'm going to write the following. Q is equal to C ops into VGS minus VT minus V of X. So this gives us the idea of the impact of the drain voltage. Okay. So yeah, all right. Now what we are going to do, we are essentially going to substitute the same old current expression that we had here over here. Just going to substitute this. That is why I did not write the linear regime current expression in this slide, because the current that we wrote here, this is fairly general. This is fairly generic. Like this does not depend on which mode my device is operating in. And that is kind of our aim also. We need a single unified theoretical model that will help us understand the different behavior regimes of the device. I don't want one current equation for my linear regime and another current equation for my saturation regime. I kind of want both of these to be present in the same integrated model. Okay, so moving on. Uh, just 1 second. Yeah. So yes. So this is the thing, and therefore I'll just write IDS is equal to W times Cox into VGS minus VT minus V of X. I can no longer make the linear approximation for the electric field. So I am going to have to write the whole thing here. So minus sign will come out here, UN into dVx by dx. Now over here I will make a couple of assumptions. First assumption is, so there are two assumptions here. So first assumption is as follows. Electric field is constant in the channel. So this is something that I still want. By constant, I mean constant up until the pinch off point. Constant up to the pinch off point. And secondly, I will also assume that, what is the second assumption? Yeah, IDS is constant everywhere. So the current is continuous. Okay. So now how do we go about deriving the saturation current? we essentially just perform this integration. So integral 0 to some L dash, and since I've assumed that the current is a constant, I can write this is equal to integral 0 to, now we don't know what the upper limit here is. We'll see that in just one moment. So there's a negative sign here, Cox VGS minus VT minus V of X into mu n times V of X dV of X dV. Now remember, the pinch off occurs when there is no more charge. Going back to the charge expression, for in the linear regime, I know this is the case. Now in the pinch off, there is no inversion charge happening, therefore this voltage has to become zero. So I am essentially looking at a point where Vx will become VGS minus VT. That is when this quantity is going to be zero. So we are going to perform the integral VGS minus VT. So all of these are like Cox and mu n are a constant. So I can drag them out too. And here I'm going to get an L dash. So L dash is the length. L dash is the length at which V ds, or rather V of X, is equal to VGS minus VT. So this is the point where my drain voltage completely nullifies the effect of VG. Now, again, if you go back and think as to what happens in the case of this, pinching off phenomena, you will notice that this effect right here, like inversion charge density and pinch off will reduce the number of electrons, so pinch off occurs. And I know pinch off is the point where E vector is zero. Now, if you remember, E vector becomes zero at kind of the top of the band in, last week's analysis. So this whole effect that we are talking here, this is actually the above effect is a consequence of DABL. Like that is essentially what is happening here. Because my drain induced barrier lowering, what it does is it kind of drags down the barrier in the channel, and because of that I have a maximum potential point where the electric field will become zero. Once the electric field becomes zero, I will no longer have any mobile charges over there, and that DIBL is essentially what is causing this velocity saturation, sorry, the current saturation as well. Okay, so that is the point. So V of X at which, yes, this is what is the this is the length at which Vx is equal to Vgs minus Vt. Now, IDS into L dash, of course, there is also a W here. Okay, so L dash to minus W into C ops into, my God, yes, UN mu n. Why is this so hard to just write the Greek symbol mu? Yes, mu n times integral 0 to VGS minus VT. Here we have VGS minus VT into V of x minus V squared, V of x the whole squared dV. Is this correct or am I making a mistake? Just one second. Oh yeah, why is there an additional V of x? That is the problem. This shouldn't be here, it's just dV by dx. Sincere apologies. See, there wasn't a Vx here, there is just this one term. Okay, so yeah, I was like, why am I getting a cubic term? Of course, there are no cubic terms. So what we have here is we have minus V of x times integral dV, like not integral dV, integral dV. Now this is going to become, I will get a V of x here, I will get a V of x squared by 2, and so that is going to give me so now this integral will evaluate to, so IDS into L dash is equal to minus W into mu n times, now this integral is going to be VGS minus VT times V of x minus V of x squared divided by 2, varying all the way from 0 to VGS minus VT. So now that will give me VGS minus VT squared minus of that, which will therefore give me IDS is equal to W divided by 2 L dash C of into mu n VGS minus VT the whole square. And this is what we saw here, mu n C of. So from this we know that lower the value of L dash, higher the value So now I can write this as ID sat directly. This is the saturation current. Of ID sat. Now higher the value of VDS, lower the value of L dash. So this gives me the relation. The higher I have VDS, the sooner I will reach Vx equal to VGS minus VT, and because of that, I will have a higher and higher and higher saturation current. So this is how the system operates in the saturation regime. Now you can see that in the case where VDS was very small, I can take this function out to be a constant and pull it out and treat Vx to be almost zero, and I will get my complete relationship for the linear regime current. Now by just treating that integral properly, we are also getting the saturation regime current. Yes. Now using the relevant parameters given in problem 1 and 2, calculate the minimum possible value of saturation current can have in the channel. Oh yes, desaturation current can have in the channel. Yes, yes, yes. Like the English is correct. For a second, I doubted my own thing, my own question. See, my own like phrasing of the question. So now I know I desat. So what does this question mean? It's essentially a continuation of the previous statement. Lower the value of L dash, higher the value of ID set. Now, what is the lowest possible value of ID set? Is W upon 2 L dash. The whole squared. Now, higher L dash implies lower ID set. But L dash always has to be less than or equal to L. Therefore, ID set minimum will be equal to W by 2L. Essentially, I'll have to substitute L dash by L. Yeah. So now just substituting the values, I will have 10 divided by 2, the micron, like just cancel each other out, into 800 into 3.45 10 to the power minus 7 multiplied by 4.3 the whole squared. So this is the value. So I don't have to worry about any more factors. The answer is going to come out in amperes. So that will come out to be yeah. So this will come out to be 0.025 ampere, which is equal to 25 milliampere. Notice that for the same device, in the linear regime, we had a current of 1.2 milliampere. However, once this device saturates, the lowest possible saturation current that such a device may have is 25 milliampere. So it is actually like around 20 times higher than the linear regime current that we observed for a conservatively chosen uh, voltage value. Okay, so that one more second, please. Pardon my obsession. Good. Yeah. So 25 milliampere is the like approximately 25 milliampere is the current that we get. Now let us do a couple of follow-up questions to this. Before we move further, this is the absolute minimum value of the saturation current. Now let me ask this question. If for the same MOSFET, I know ID sat is equal to 35 milliampere. Let us say I know that. Then, like, find the following values. So this is another kind of numerical we can have. So A, find the L dash at which pinch off occurs. The second question is find the value of VDS for the same current. Okay, so now I know at L dash equal to 10 micron, 10 micrometers, we have ID sat to be 25 milliampere. So question is at what L dash will we have ID sat to 35 milliampere. Now we know that ID sat is inversely proportional to the effective channel length, even in this expression. Even in this expression, yeah. So this is the value for ID sat. Even here we know that it is inversely proportional to L. So all I need to do is take the reverse ratios. So therefore This implies 35 by 25 is going to be equal to 10 micron. Oops. I am sorry, this is not 10 micron, at 1 micron, because 10 was the width of the channel. So now this is 1 micron divided by the L dash for the case that we are concerned. So therefore that will give me L dash is equal to 25 by 35. So that is going to be 5 by 7, which will come out to be 0.715 micron, or around 715 nanometers. Okay, so this is the length of the channel. Now, oops, this is part A. So these are the answers. Okay, so now what about part B? I need to find the drain source voltage for which the same happens. Now, how do I go about doing that? So for that we will use the following assumption. Epsilon x is a constant in the channel. Okay, so this implies VDS divided by the total length of the channel. Now that is the potential difference, like that is the effective electric field between the source and the drain. Right. Yes. Now this has to be equal. Essentially what I mean is the following. Let me go back in. Like in both these cases, the electric field wherever the inversion layer has occurred is going to be the same. Like that is the thing that I demand. Wherever I have an inversion layer, the electric field has to be the same. So for the previous case, we had like an electric field of VDS by L. Okay, so not in the previous case. So VDS by L should also be equal to VDS minus V of X divided by X for some intermediate point, for some intervening point. Okay, because like I know two things, Vx equal to Vgs minus Vt at the pinch off point. And everywhere here, I will need my electric field to be a constant. So I can still take a linear approximation. So yeah, of course, here the assumption is it is assumed potential has a linear profile, of course. And this is not an entirely unfair assumption. Like unless we have very extreme cases, this is more or less going to be true. What am I writing? Linear profile. Okay, so then all I have to do is substitute this over here. So the denominator here is 1. So therefore VDS is equal to VDS minus VGS minus VT divided by 0.71. I'll drop the file for a second just to make life easier. So this would imply 0.71 VDS is equal to VDS minus 4.3 volts. VGS minus VT is 4.3, which further implies therefore VDS is 4.3 divided by 1 minus 0.71. So this is going to be so this will come out to be 14.83 volts. So as you can see, this kind of look at it this way. And for the previous case also, you can do the same calculation. Although over there, so let us do that also. So for IDSAT equal to 35 milliampere, I know VDS is 14.83 volts. Okay, we have someone joining somewhat late. Nonetheless, welcome to the session. So we have IDSAT is equal to, for IDSAT is equal to 35 milliampere, we can derive that VDS is 14.83 volts. Now, additionally, I can go to the previous problem and ask the same question. Essentially, in the case where I have 25 milliampere, what would be the case for, what would be the value of VDS? I will do the same derivation. Here, this length is going to become 1 micron. So, wait, in that case, I have VDS is equal to 0. No, I will not have VDS is equal to 0. What will that come out to be? So, VDS minus 4.3 is going to become, oh yeah, of course, it has to be. So in that case, VDS will be 4.3 volts. So for IDSAT min, minimum, which is equal to 25 milliampere, I know VDS is equal to 4.3 volts. So to increase my current saturation, like beyond saturation, to increase my current from 25 milliampere to 10 milliampere, to have a 10 milliampere increase, I would need much more than like a 10 volt increase in the voltage. Now, previously, if you would have seen like the for the same device, where were we in the linear regime? So in the linear regime, yes, here we are. We had 1.2 milliampere at 1 volt. Okay, so just to get a qualitative picture of what is happening, I have 3 data points with me now. Let me try plotting that to see how this current profile looks like. So yellow is a bit hard to see sometimes. Yeah. Oh, come on. Snap on, please. Okay. So how is this current profile going to look like? Well, technically I have 4 data points because I know at VDS equal to 0 there is no current. Okay, so and let me say this is like I have up to 35 milliampere. So let me say this is 40 milliampere. So this is IDS in milliampere, and this is VDS in volts. So this is 40, that means this is 20. And how many points do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 for every 10. So every single, like, oh no, this is actually split into 10. So every step is going to be 2 milliampere. Okay, so there are like 10 spaces here. So every step is 2 milliampere. So this is, yeah. So at V equal to 0, I have I equal to 0. Then, so VDS, let me make it, so VDS, I will have to make it significantly smaller. So let me make it steps of, I need to go up to 15. So let me make it in steps of 5, 10, and 15 volts. Yeah. So so 2 steps here will be 1 volt, right? Yeah. So this is going to be 1 volt, and at 1 volt, I know the current is very close to here. So let me make a small dot over here. Okay, and then at VDS equal to 4.3, I know ID sat becomes 25 milliampere. So I am going to have 25, which will be somewhere over here, and 4.3 is going to be somewhere over here. Yeah. Oh no, 4.3 is going to be like 4.8. Oh no, each is going to be 0.5. So yeah, somewhere over here. Yes. So this is going to be the second current point, and then a further increase all the way here will only take me up until here. So this is how the current profile looks. The linear regime, my current is increasing like this, and after the linear regime, my current is increasing like this. So with just these 3 data points, we are getting this kind of a profile, which is what we expect to see in the saturation, behavior of my uh, transistor. So 4.3 volts is the VD sat. So this is 4.3 volts over here, approximately. And at this point it is increasing by this much. So previously, by just moving 4 volts, I gained like 23.8 milliamperes. So that was the effective resistance in the linear regime. And in the saturation regime, it is essentially behaving as a channel with a significantly raised resistance. So this gives me my linear and my saturation regime in a more quantitative manner. Like I've chosen real values. So this is my linear regime and this is my saturation regime. So the equations that we have, namely this equation right here, this integral right here, and this condition L dash at which Bx becomes Bgs minus Bt, and then the linear regime current, which is this quantity right here. All of these are, more or less correct. They are giving me the right quantitative description of the device. So I'm able to observe the linear behavior, the saturation behavior, and all the associated things in this unified model. So this brings us to the end of the discussion on the transistor MOSFET characteristics. So now let us go back to the ballistic channel very briefly. So this is the last topic for today. This discussion I'm going to do directly through a problem. And with this, I think next week we should be ready to talk about the ballistic MOSFET. So first, derive the expression, not first. The only thing that we are going to talk about here is to derive an expression for the uh, unidirectional thermal velocity in a 2D ballistic channel. How will this expression change for a 3D channel? So that's kind of the question. So now unidirectional thermal velocity here, by unidirectional I mean of course drain to source, or rather source to drain. Now why am I so concerned about the thermal velocity? You'll see in a second. So now how do I calculate these quantities? So how we do that is the following. So first we have, like, essentially any average velocity is going to be integral V. First let me write the following. Let us say V is equal to, or is defined as, V of energy, temperature, and the angle theta. Okay, so E is energy, T is temperature, then I have the angle theta. Now, why am I suddenly talking about theta? Remember what a ballistic channel looks like. Again, all of this is 2D ballistic channel. So in this, I know that the electron can enter with any angle. So this is the velocity, and let me make this slightly clearer. In fact, I think I know what I can do here. I can resize this whole thing. Yes. Yeah. Now things can be made clearer. Oops. Now let us say I have an electron that is entering with this velocity. Then this is the angle, and of course this direction is the x direction. So this is the source to drain direction. I have my source here, I have my drain here. So this is kind of how we are looking at the channel. Therefore, the quantity theta is what I shall call the injection angle. Again, let me remind you, we are talking about ballistic channels now. So the electron, I'm treating it as a point particle. It has a velocity, it enters the channel and it reaches the drain without undergoing any collisions. So the electron is injected at a certain angle and it has the following, like, of course the velocity will depend on the energy and also the temperature maybe may not be. Okay, so I don't know like what the relationships there are. So these are the potential parameters. Now to find the average of this velocity v in general, what I will have to do is I will have to integrate v e comma t comma theta with respect to some distribution function h e comma t comma theta. So this will give me the distribution. Of course, when the temperature across the channel becomes a constant, this quantity will like not vary anymore. d d theta divided by integral h of e comma t comma theta d theta. So wait, why am I doing that? I can just erase the thing myself. Yes. Okay, so this is how it is going to be. And what is this h of e comma t comma theta? So that is some distribution function. It's a distribution function which determines what is the likelihood, what is the probability of my electron entering at a certain angle, my electron having a certain energy, and the temperature having a certain value. These are the parameters that can vary inside a channel, potentially vary inside a channel. Temperature is usually a constant. I can also write that. Um, then you can ask, why am I mentioning temperature here? Because in a couple of weeks we shall look at the thermoelectric effects and things like that. So to account for that, I'm kind of just mentioning it here, just to make you aware of the fact that temperature can also play a role in these parameters, these quantities. So okay, now that gives me the dependence. So ultimately, now I need to find out what the h here is. All right. And the integration, of course, takes place over an appropriate range. Okay. So now one thing that I know is, let me, yeah. So one thing that we have already assumed is a previous assumption. It has been previously assumed that theta distribution is uniform. What do I mean by this? It essentially means V does not depend on, is independent of theta. So this is something we have already assumed. So right off the bat, I can just go back to my old result. V plus with respect to theta is 2 by pi V of E. This I know. This I know already. So this has been derived like several times, and we know what all these quantities stand for. Wonderful. So this part is already done. Now additionally, I also know the following. I know V of E is equal to 2e upon, wait, it should be square root of 2ab. Oops. Right? Yeah. Square root of 2ab is the momentum. Of course, it is going to be 2e upon m star. I hope this is clear. Whole power half. Like this, I have, since e is equal to half mv squared. Just for the sake of clarity, I'm writing it here. Although by now all of us should be familiar with this. Okay, so this part is also something that I know, so I can substitute it further in and go v plus averaged with respect to theta is 2 pi v of e, oops, 2e by m star whole power half. Yes, so this we know. Now we just need to integrate over. The temperature is a constant, so I don't worry about that in this case. So the only thing that I'm concerned about is the energy distribution, the distribution of energy. Now, what is the energy distribution function depend on? So that will actually depend on, so energy distribution. Essentially, how the question is how many electrons with this energy E will I have? F of E. So that is what it is going to be. It is going to be the density of states multiplied by the Fermi distribution function. So therefore, the averaged unidirectional velocity is going to be the following. Per half into m star upon pi h bar squared into the Fermi function, which is 1 plus e to the power e minus ef upon kbt dE with a denominator not to be forgotten in this case. So what is the denominator in this case? The denominator is going to be integral 0 to infinity m star, into, so I'm just going to write this in the short form because I don't have much space over here. EF upon QBT whole power minus 1 DE. Okay, so that will tell me that. Now this is a constant. this quantity here is a constant, and I know the integral of the Fermi function is 1. So I can very directly say the following. Like, this quantity will jump out, this is also going to jump out, they are going to cancel each other. The denominator integral is going to become 1. So all I'm left with is upon m star per half into 1 divided by 1 plus e to the power e minus ef upon kBt dE. Now I'm going to make the following substitution. I'm going to say E upon kBt is eta, therefore dE is kBt times eta d eta, and additionally what I'm going to do is, of course, along with this I'm going to say EF upon kBt is equal to eta f. And you can guess where we are going with this. Okay, so this is my change of variables. So two by pi into kBt into, so I'm going to have to multiply and divide by kBt here. So I will have 2 divided by kBt, m star kBt, per half integral 0 to infinity eta to the power half divided by 1 plus e to the power, eta minus eta f d eta. Yeah, so all the constant terms have been extracted out. The kBt is also going to cancel with that factor. So what we will have is the following. Two by pi into 2 kBt upon m star whole power half into this integral here. Now, if you can recall that this looks like a Fermi integral. The only thing that is missing is, to define a Fermi integral, I will also need the gamma function. And what is the gamma function that I'm going to need? The gamma function that I shall be needing is, so let me just write the definition here. So Fermi of n, Fermi integral of order n is 1 upon gamma of n plus 1 integral 0 to infinity eta to the power n dx 1 plus exponential eta minus eta f deta. This is the Fermi integral. So I will need a factor of 1 over gamma n plus 1. In this case, n is equal to half. I know gamma of half is root pi. So this is a known quantity, square root of pi. And I also know gamma of n plus 1 is equal to n times gamma of n, which implies gamma of 3 by 2 is square root of pi by 2. So I will need a reciprocal factor of 1 by gamma of 3 by 2, which is equal to 2 divided by square root of pi. And it is very convenient that I actually have that with me here. So I have 2 by pi, I just need to take a square root of pi out. So times this integral again, let me write this one last time. Eta to the power half 1 plus eta minus eta f deta. Now I will just take the 2 upon root pi over there, turn that into a Fermi integral. I will have a root pi which I will absorb into this. So I have 2 kBt upon m star, pi m star. Over half times this Fermi integral f half. So this is the unidirectional thermal velocity in a ballistic channel. Two D ballistic channel to be more exact. And what we can say, like, although I am not talking about this in detail over here. Oh yeah, one more thing. So I will need a new slide for that. So this quantity here, 2 kBt by pi m star whole power half. This quantity right here, this is the average thermal velocity. So if you are familiar with Maxwell-Boltzmann statistics, then we can define like multiple velocities. We can get like VRMS, root mean square velocity, and average velocity and other quantity. So this is the average thermal velocity for a 2D Maxwell-Boltzmann gas. Oops, why am I writing two S's? Gas. So this quantity is actually this. This is integral 0 to infinity V integral e to the power minus m v squared to kbt divided by integral dv. Of course, there will be a normalization factor for this Gaussian. So I will say this is proportional to this quantity. Or wait, the normalization factor will actually cancel each other out. Yeah, I can write it like this. E to the power minus m to kbt. If you perform this integral, you will actually get this value right here. As you can see, like, I just need to substitute for the Gaussian and parameters for the Gaussian integral, and the normalization factor is going to be 1 upon root 2 pi. So that will appear somewhere over here in the denominator over here. And here I can, set v square equal to t, and this will become an exponential integral. And you can actually see that you will get this value over here. So this is exactly this integral. So this is the average classical velocity. So what we can see is in our semi-classical approach, of course, since it is semi-classical, and even if we try to do an exact approach, this answer actually comes to be pretty close. The classical thermal velocity multiplied by a Fermi integral is what gives me the complete ballistic behavior. Okay. Oh yeah. Oh yeah, I forgot. So I also need uh, yeah, so this is what we will have. Yeah. So now what will happen for in the case of a 3D system? I am not going to do the derivation again. Suffice it to say, 3D system, what we will have to do is go back here and look at this expression right here. Over here, I will replace this by the 3D density of states, and therefore there is going to be an e to the power half over here and an e to the power half in the denominator. All the other factors will cancel each other out. So essentially this quantity 3D system V plus is going to be proportional to F1 divided by F half. Okay, so similarly one can ask what is going to be the in fact I think more or less no, I will not get all the factors there. I will get, I think, a couple more values. So the constant of proportionality may be next session if it is necessary. I will tell you what the constant of proportionality is. But this whole, ratio of Fermi integrals is what we have. In fact, even here you can see that this is actually f half divided by f0 because f0 is 1. The Fermi integral of order 0 is a constant, it's 1. So this is f1 by half. Now you can guess what will happen if I have a 1D system. So this is actually equivalent to 2 kBT upon pi m star into half into f half divided by f0, and this is a constant. So I have half in the numerator, 0 in the denominator for a 2D system. I have half in the denominator, 1 in the numerator for a 3D system. Observe the pattern and you can guess what is happening for a 1D system. So you may be asked questions like that, where you're given a 1D, 2D or 3D system and you're asked to find the unidirectional thermal velocity, average thermal velocity. So this kind of is the starting point for the analysis of the ballistic MOSFETs. So next session we shall talk about how the ideas of current saturation and linear behavior and all these things appear in the case of a ballistic MOSFET. What we have discussed here so far in like the first 80% of today's session or 60 to 70% of today's session is classically understanding the linear and the saturation behavior of a MOSFET. We have derived the equations, we have even solved numericals, and we have somewhat quantitatively seen how these two behaviors look. We have actually done some number crunching and we have arrived at the values of currents and voltages, and we are seeing that how saturation is occurring. And in the end, we have gone through one derivation for the unidirectional thermal velocity. Although this derivation may look ad hoc right now, next week this will fall more into context. Okay, with that, I will end today's session. I thank you all for attending and watching. We shall meet again, same time next week. So let me pause the recording. Yeah, so thank you for attending.